and stuff. So while this is adjacent, we do tons of stuff on space tech and stuff like
that's
that.
nice.
So this is not as far off the lane as you might think. And obviously, we've got an audience full of nerds. So this is
Well, I know your audience because I used to visit Silicon Valley very often in before the pandemic. You know, I'm chair of the Starshot, the Breakthrough Starshot Initiative. And
yes, you know what? And you know what? I don't like to be formal about this, so let's consider ourselves recording. I do want to talk to you about that at the end, so I'm going to try to make sure that we make time to squeeze that in.
sure, anything you want to ask me on any.
Yes.
If I don't know the answer to, I'll say I don't know, but you can ask me anything.
Well, if you don't know the answer,
Think of it as a jazz concert where you can improvise.
All right, well then let's just go right into it then, because listeners to this show also know that I'm a big fan of like the Fermi paradox, great filter, you know, the Drake equation, all that stuff. So I remember when this happened, but why don't you just catch us up real quick? So back in October of, what was it, 2017?
Yes.
We had a historic event. So tell me just real briefly, like set the table for us.
Right. It was the Pan-STARRS telescope in Mount Haleakala in Maui, Hawaii, that discovered while surveying the sky for killer asteroids that might come close to Earth to endanger us. While doing that, they discovered the first object that came from outside the solar system. It was moving too fast to be bound to the sun, and it was given the name Oumuamua, which means in the Hawaiian language, a scout, a messenger from far away. And of course, the astronomers at first thought, we've seen rocks from the solar system throughout history. This must be a comet. These are the most common rocks that are covered with ice. And when they get close to the sun, the ice evaporates and creates a cometary tail. The only problem is, while monitoring this object, there was no cometary tail. As it was tumbling around, its brightness changed by a factor of 10.
Well, let me interrupt you there, because let's go down the line of why we knew that this was unusual. So, like, first of all, you said that it was moving faster than would be natural if it was tied to the sun's gravity, right? So that's how initially you knew that it was outside it came from outside the solar system.
Right.
So so we've never ever seen anything like that happen before. Everything we've seen has been always tied to the sun's gravity.
Right. The point is, you need a big enough object that reflects enough sunlight for you to see it with our existing telescopes. And you need to monitor the sky, a big chunk of the sky, for a long enough period of time before you see the first one. Now, a decade earlier, I actually wrote the first paper that forecasted how many such objects should we expect from interstellar space based on what we know in the solar system. So the solar system loses rocks to outer space as a result of passage of other stars, or as a result of scattering by the planets. And we estimated that Pan-STARRS, this telescope, would not see anything because they are just too rare. But the next telescope, which is called the Vera Rubin Observatory, that will start operations in 3 years, should see some. That was the expectation. And then they discovered Oumuamua while surveying the sky. That was a surprise, because it means that such objects are much more abundant than we expected.
And it also intercepted the orbital plane, right? Is that also unusual, like that? Okay.
That's typical for anything that comes from outer space, because it doesn't know anything about the orbital plane of the planets.
So, but the key was that you weren't seeing outgassing like you would expect from a comet or something like that, right?
Well, so there are another type of objects called asteroids that are just rocks without any ice on their surface.
So there would be no outgassing.
Then the astronomer said, okay, it's not a comet, therefore it's an asteroid. The only problem with that is that there was an extra push exhibited by the orbit. Such a push could be given by evaporated gases, the rocket effect in a comet case. So on the one hand, it exhibited the kind of push you see in comets, but then it wasn't a comet. It needed to lose about 1/10 of its mass to produce the extra push that was observed, but there wasn't any trail behind it. And the Spitzer Space Telescope searched very deeply and put very tight limits on carbon-based molecules or other types of dust particles around it. And at the same time, it was not just an asteroid, a rock, because a rock would follow an orbit shaped by the force of gravity alone. And then the question was, what gives it the extra push? The only thing I could think of is reflecting sunlight. So the sunlight itself is giving it a kick. And for that to be effective, you need the object to be very thin, sort of like a sail on a boat. And that is called a light sail. And we are using this technology now in the context of space exploration. We are trying to develop it because the advantage is the spacecraft doesn't need to carry the fuel with it. It just reflects light. And as a result, it gets propelled. I should mention another unusual property of this object, and that is when astronomers try to model the light curve, the reflected light as a function of time of this object as it was tumbling around over a period of 8 hours. The brightness changed by a factor of 10, and the best fit model was for a flat object, not a cigar shape. This was depicted in some cartoons, but a flat object that has extreme geometry, that is very thin relative to its length. And to me, that sounded just like a light sail.
All right, so I'm gonna sum up the weirdness here. So no outgassing, not a comet. Its speed doesn't make sense because when it speeds up after it goes around the sun, it speeds up too much to account for the gravity kick that it should have gotten. It is exhibiting weird light because like if it were a rock or something else, like you wouldn't see a 10x factor in terms of the light. And then the shape. So what you're describing is, you said like football field, but it has to be really thin. So you'd have to imagine like a pancake that's the size of a football field, right? Is there anything that you or anyone has ever seen that would have naturally had such a giant pancake shape?
That's an excellent question. So when we wrote the paper, and to me, it sounded like the most plausible explanation is that it's artificially made because nature doesn't produce such thin slices. In the following couple of years, mainstream astronomers tried to explain it from a natural origin. And the scenarios they came up with are always associated with something that we have never seen before. For example, a hydrogen iceberg, frozen hydrogen. We've never seen that. We don't know how to make it. Moreover, I wrote a paper afterwards with a collaborator of mine showing that such an iceberg would evaporate very quickly as a result of absorbing starlight along its journey that takes millions of years. So it doesn't make any sense to consider a hydrogen iceberg. And then there was another suggestion that maybe it's a collection of dust particles, kind of a dust bunny of the type that you find at home, except the size of a football field, and very rarefied, very porous, 100 times less dense than air. So a cloud of dust being pushed by reflecting sunlight. Again, to me, it sounded like such an object would not survive the journey. Then there was another suggestion of the mainstream saying, oh, maybe it is a fragment, a shrapnel from the disruption of a bigger object. But a shrapnel, if you disrupt the bigger object by, for example, a star, it ends up being elongated, not flat. Finally, I should say that all of these peculiarities, when you add them together, each of them has a small probability, and then they add up together to become an extremely unusual object, and definitely something that we have never seen before. So if we have never seen it before, why not contemplate an artificial origin?
Right. There's one more odd thing about it that you go into in depth in the book, and maybe it's a little complicated to try to squeeze in here, but explain also the unusualness of the speed and this concept of the local standard of rest.
Right. So when you average over the random motions of all the stars in the neighborhood of the sun, you get to the local standard of rest. It's sort of like the galactic parking lot. And if you find a car parked there, you can't tell which house it came from, which star did Oumuamua come from, because only 1 in 500 stars is so much at rest relative to the local standard of rest as Oumuamua was. So it was sitting still, just like a buoy on the surface of an ocean. And then the solar system, like a giant ship, ran into it. So the relative speed was just because the sun moves relative to the local standard of rest.
Right.
And
So
that's quite unusual, because only 1 in 500 stars is so much at rest. And moreover, it leads you to wonder what the purpose of this object could have been. It could have been a member of a grid of objects that are used as signposts for navigation, in interstellar space, or it could be a relay station. Who knows?
right. So the easiest theory is that, like you said, this is a light sail that could have been shot towards us, but also by the fact that it essentially was sitting there stationary relatively in space, it's also likely it could have been some form of you said space buoy, but it could be any form of like even space garbage that we just happen to run past, right?
That's
Uh,
right. It could
yes.
be trash, yes. And it could be the surface layer of a spaceship, something that is very thin. I should say that in September 2020, just a few months ago, there was another object found which exhibited a push by sunlight without a cometary tail. And astronomers traced it back to a 1966 launch of a lunar lander mission, where the rocket booster was kicked into space, and the object that was found was just this rocket booster. So this illustrates the fact that we can tell a thin object pushed by sunlight from a comet. We can tell the difference between a rock and a hollow object that is very thin, based on the fact that there is no cometary tail and the object exhibits an extra push. And to me, that illustrates the possibility that Oumuamua was artificially made, because this rocket booster was produced by us. We know that. But Oumuamua could not have been produced by us. It was moving faster than any rocket we could launch. And the question is, who produced it?
Right. So whether it is an intentional probe or something sent towards us, whether it's just an artifact that we happen to run across, you're making the argument in the book that we should essentially make a wager that says, who cares? Let's assume it was an alien object, because if we're wrong, there's no real downside. If we're right, we potentially stand to make one of the greatest and most radical and valuable discoveries ever made by science.
Exactly. And my surprise really was, I followed the scientific approach that I apply to any other anomaly that I encountered throughout my career. And I've worked on the first stars in the universe, the early universe. I worked on black holes. I worked on dark matter. We don't know what most of the matter in the universe is. And when there were anomalies, I suggested explanations. And then the way forward would be to collect more data, more evidence, and figure out, just like Sherlock Holmes looking at evidence in the crime scene and trying to use all the clues to figure out which possibility remains on the table once you look at all the clues. And the same is true about Oumuamua. I applied the same approach, but to my surprise, there is a taboo on discussing this possibility in the scientific community. And I find that really unfortunate, because we now know that about half of the sun-like stars in the Milky Way galaxy, based on the Kepler satellite data, half of them roughly have a planet of the size of the Earth, roughly at the same distance as the Earth is from the sun. And that means that you could have liquid water on the surface of the planet and the chemistry of life as we know it. So not only that we are not at the center of the universe, as Aristotle argued and was wrong, but moreover, what we see around us in the backyard, a sun-Earth system, is extremely common. And that means, to me, if you arrange for similar circumstances, you get the same outcome. Why should we be unique? That's an arrogant view. My approach is modesty. Let's assume that, let's be modest and say we are a typical outcome. And then all we need to do is search for those signatures of other civilizations. But somehow, for some reason that is beyond me, the mainstream of the astronomy community argues that this should never be discussed. And to me, that's appalling, because the general public is extremely interested in this question. We have the scientific tools to address it, And how come the scientists shy away from this subject? And, just to give you an example, the astronomers are designing future observatories that would look, for example, for oxygen in the atmospheres of planets around other stars. Now, oxygen would not be necessarily an indication for life because the Earth didn't have much oxygen in its atmosphere in the first 2 billion years. For half of the age of the Earth, there wasn't much oxygen, even though there were microbes on the surface. There was life. So not finding oxygen doesn't tell you that there is no life. But moreover, if you do find oxygen, it can be produced by natural processes, like breaking up of water molecules. What would be a signature of life that would not be disputable? If we find industrial pollution in the atmosphere of the same planet. And you can use the same instruments, the same observatories, but you will never hear an astronomer saying, let's build this observatory to search for industrial pollution. And I don't understand why, because that would be an obvious signature of life, because nature cannot produce these CFC molecules that are produced by refrigerating systems and the industries here on Earth.
I like the point that you made that there's, while things like SETI are sort of looked at as like the maybe on the edge of crackery because there's no evidence, you point out that there's a lot of stuff in physics and in science where there's not a lot of evidence, and yet the theories are broadly accepted, like in things like quantum theory and stuff like that. So, if every time scientists say, well, SETI is crackery because there's been zero evidence, but that doesn't mean that you still shouldn't look.
Well, the situation is worse. I would say that there is a lot of, ridicule towards people that consider technological signatures. I don't care how many likes I have on Twitter. I have a well-established scientific career with more than 800 papers. I was chair of the Harvard Astronomy Department for 9 years, the longest serving chair. It was renewed twice. I'm chair of the board on physics and astronomy of the National Academies. I have a lot of leadership positions. I don't really need the approval of others to make my point. But the issue is really that this subject is ridiculed when, as I said, it's quite likely that we are not alone. Whereas in the same physics community, you have ideas like the multiverse, extra dimensions, string theory that are celebrated by the mainstream. And, theoretical physicists give each other awards and are very proud of the mathematical gymnastics that they are making. And I understand it in terms of showing off. They are trying to show how smart they are, and they don't care what nature is. They don't care if nature has extra dimensions. They don't need feedback from experiments. My point is that physics is a dialogue with nature. It's not a monologue. You're supposed to listen to nature, look at experiments, and then revise your notions about reality. And you might be wrong. Einstein was wrong 3 times at the end of his career in the last decade. He argued that black holes don't exist, gravitational waves don't exist, and quantum mechanics doesn't have spooky action at a distance. Now, why was he wrong? We know that from experiments that he was wrong. He was wrong because he was working at the frontiers and he was willing to put skin into the game. He was making predictions and they turned out to be wrong. Now, my colleagues in string theory, the colleagues that work on the multiverse, on extra dimensions, they don't put any skin in the game because there is no experiment that is testing their predictions. But moreover, that they don't even want experiments. They claim it's complete. Maybe we should revise the way we interpret physics. We can work in anti-de Sitter space, which is a space that does not represent reality as we know it. And they can do mathematical gymnastics, show that they are smart, give each other awards, honors, membership of honored societies. And it's all for the benefit of showing off. It's not for the benefit of understanding nature. And my point is that every physicist, just like a medical doctor, should make an oath. I call it the Galilean oath, which basically says that at least one of the ideas that that person works on will be testable within that person's lifetime. Otherwise, it's just like taking drugs and imagining a much more beautiful world and, not even caring about reality. We can all think that we are wealthier than Elon Musk. We can think that. But once we go to an ATM machine and want to use our money to buy something, we realize that our bank account is different than what we argued it is. And that's called a reality check. That's what experiments give you. And I find it completely unhealthy for the scientific community to endorse within the mainstream ideas like multiverse or ideas like extra dimensions that have no substantiation in any experimental fact, while at the same time pushing back on any discussion about technological signatures. Now, when you don't fund searches for those signatures, when you bully young people that work on those, then obviously it's just like stepping on the grass and claiming, look, the grass doesn't grow. It's a self-fulfilling prophecy.
Speaking of things happening within our lifetimes, and actually speaking of solar sails and things like this, I really want to make a few minutes to talk about. Well, Uri Miller is a name that Milner is a name that a lot of people in Silicon Valley know, because he's sort of one of us, as it were. So tell me about Uri and this Starshot initiative, because I'd heard about it, and so I want you to describe it, but I want to know where that is today as well.
Sure. So Uri came to my office at Harvard in May 2015 and asked me, Avi, would you be willing to chair a committee that would look into the possibility of visiting the nearest star, which is 4 light years away, within our lifetime? Now, Uri is exactly the same age as I am. What that means is within 20 years, getting to the nearest star, Proxima Centauri, which later on was found to have a habitable planet around it. Now, if you want to make it in 20 years, you need to launch a spacecraft that moves at 1/5 of the speed of light. So I told Uri, look, I will look into that in the next 6 months and get back to you. And together with my students and postdocs, we arrived at the conclusion that the only technology that can do it is the light sail technology, where you push on a sail the size of a person with a very powerful laser beam that is focused on it of 100 gigawatt for a few minutes, and that sail can reach 1/5 of the speed of light if it weighs only a gram or so. So that was the concept. I presented it to Uri. He was very excited. We announced it in April 2016, together with Stephen Hawking, that came especially for this occasion, and also to inaugurate the Black Hole Initiative at Harvard that I'm serving as the founding director of. And then after that, we started focusing on the various elements of this technology. One of them is what we call the photon engine, the laser beam, how to produce a coherent, powerful laser beam from combining a lot of less powerful laser beams. The second has to do with the sail, how to produce a stable sail that rides on the beam of the laser without absorbing much of the light so that it doesn't burn up. It needs to reflect almost everything that impinges on it. And then what kind of geometry and what kind of composition to give to that sail. And so that's the second challenge. And the third major challenge is communication. Once this spacecraft gets to a distance of 4 light years, it's very far away. How to communicate the photographs that are taken of, let's say, a habitable planet around Proxima Centauri to Earth. So that's the third challenge. But I should say that it's not just about taking a photograph of a planet around another star. It's more about getting out of the solar system. And to me, that's a dream. And currently, we're working on developing the technology. We're making the first steps in that direction. But in general, I think exploration of space is the future of humanity, because currently all our eggs are in one basket here on Earth. We will need to spread them. It's just like the revolution that came about from the Gutenberg printing press. You know, before that, there were only a few copies of the Bible that were handwritten, and each of them was precious. But once the printing press came along, then there were many more copies. And if something bad happened to one of them, it wasn't a catastrophe. And the same thing applies to life on Earth. Currently, if a catastrophe takes place on Earth, we are doomed. Nothing will be left behind from what we value. But if we were to spread it around in other places, then a single point catastrophe will not be as damaging.
Well, see, first of all, the thing that blows my mind about this project is I always assumed that it would be generations and generations, if ever, that we could visit another star. The part that blows my mind is we technically have the technology right now to within 20 years have visited another star.
Right.
And it's also, I mean, it's expensive, but we're talking about like potentially in the neighborhood, the final project would be $5 to $10 billion. So that's not, again, $1 trillion.
No, and it's very inspiring. Since the Apollo mission, we haven't had an inspiration about going to space. My wife, at the time that we announced the project, my wife brought the car for oil change, and the mechanic asked her, "Where is your husband? Why didn't he bring the car?" And she said, "Well, he's announcing this project Starshot in New York City." And the mechanic said, "Wow, I can't believe it. I followed every detail of this story. I'm really excited about it." So I think the public cares about space. The other thing I would mention is I participated in a debate about the space race, whether the space race between the US and China is good for humanity. It was organized by Bloomberg News and IBM a couple of months ago. And all the other debaters were worried about the military threat that is imposed by the space race. And I just couldn't understand it, because they were talking about things hovering above the surface of Earth, which is a two-dimensional surface that we live on. But space exploration is actually going in the third dimension, far away from Earth. If you go to Mars, or if you go to another star, there is no military threat on Earth. And how can we be so narrow-minded as to worry about what happens just around Earth when space is so huge? And the lesson that we can learn from Oumuamua in particular is that other civilizations may have sent things out. And perhaps we've witnessed one of those pieces of equipment that were launched into space.
Right. And listen, going to Mars is great. Going back to the moon is great. But like doing our own Oumuamua sounds to me way more exciting than that. Again, this project is still moving forward? Is it getting funding and things like that? Or are you hopeful?
Yeah. So Yuri Milner is committed, and there are teams working on the three challenges that I mentioned. It's a long-term project. It's not clear how quickly we will converge with a feasibility test, but I think it's something that we should all strive to accomplish, because like Oscar Wilde said, all of us are in the gutters, but some of us are looking at the stars.
Zuckerberg, wasn't he on the board of this at some point as well?
Yes, he is.
Okay, so listen, let's have the word go out here to Silicon Valley. All the Zuckerbergs and the Elon Musk of the world, get on board with this project. This is the exciting one.
I should say one more thing.
Yes.
I appeared on Joe Rogan just a few days ago, and as a result of that, there was a crowdfunding effort initiated, grassroots, from someone I don't know, initiating a project to experimentally scientifically test all these reports about unidentified flying objects. So people talk about the Pentagon Papers and all kinds of documents that were hidden behind closed doors and were classified, and at some point will be released and we can look at them. To me, that makes very little sense. Who cares what people reported with all the instruments from decades ago? What we want to do is go to the same sites where the reports came from and use the most modern instruments that we can use, scientific instruments, not instruments that pilots had by chance in their cockpit, but rather use the very best scientific instruments, deploy them at those sites, and see if there is anything unusual. What could be simpler than that? Why worry about documents? I don't care about all documents. And to do that, it will cost tens of millions of dollars. And there was an initiative as a result of my discussion with Joe Rogan to raise those funds so that we can initiate such a project. And the data will be open to the public.
Well, all right. I don't care how it gets done. Crowdfunding, Mark Zuckerberg, whoever. I don't care. Let's just. This is an exciting project. The most exciting one. This is an exciting book too. Again, it's extraterrestrial. The first sign of intelligent life beyond Earth. Dr. Loeb, thank you for coming on to talk to us about this.
Thank you for having me.